Alright, in this video we're talking about section 4.2 cumulative distribution functions and expected values. So the CDFs of continuous random variable is very similar to the idea that the CDFs of discrete random variables we talked about before in the discrete random variable section. Now let's take a look at the definition here. The cumulative distribution function f of x for a continuous random variable x is defined for every number x by f of x is equal to the probability that x is less than or equal to x value here. And of course, that would be equal to the integration from negative infinity to x, because x is the upper bound of this interval here, and fy dy. So for any y between negative infinity to x here. So we know that when we worked with the discrete random variables, we know f of x is equal to the probability that x is the capital X is less than or equal to the value x, so which is equal to the sum of for I would say for y is less than or equal to x, and then p of y, and that's how we that's right. So that's how we find the CDFs of a discrete random variable. And as what I mentioned in the last lecture video, we know that the main difference between the discrete random variable and the continuous random variable is that instead of doing summation, we're going to do the integration here for the CDF of a continuous random variable. And it says that for each x, f of x is the area under the density curve to the left of x. So just always keep this idea in your mind. You can always find that x is less than or equal to a number from the CDF directly, okay? But if you want to find something like probability that x is greater than or equal to a little x of you cannot do that you cannot figure this out from the CDF directly. But what you need to do is we think the opposite of it. So that would be equal to 1 minus the probability x is less than x, and which is equal to 1 minus f of x. So we don't have to worry about the equal sign here, because the probability of a single point is always equal to 0, as what I mentioned in the previous video. So that's pretty much the definition of a cumulative distribution function, and it's very similar to the idea we went over before in the discrete random variable section. And once again, the main difference that we are doing the integration here instead of a summation. Now, once this makes sense to you, let's take a look at example. I gave you that. Let me take a look at it. Where is it? It's over here. So I gave you that the PDF of a continuous random variable f of x is equal to 1 over b minus a for x between a and b, and 0 otherwise. So based on what we learned in the previous lecture video, this kind of distribution is called a uniform distribution, okay? And we want to find the CDF of x. So if we want to find the CDF of x, we just go back to the definition here, okay? So f of x would be equal to the probability that, we don't have to do that, yes. X is less than or equal to little x, so which is equal to the integral from negative infinity to x, and then f of y dy. Okay, and since we know that the x value starts with a, so this would be equal to the integration a to x f of y dy. Because for any x value less than a, or on the left side of a, the PDF would be 0. Okay, and we see a very similar example in the previous video as well. Now, once we have this, we just need to go ahead to do the integration over here. So that would be equal to integration from a to x. We put the expression of the PDF back into the integration here. So 1 over b minus a dy, right? So that would be equal to 1 minus b minus a y from a to x, and then that would be equal to 1 over b minus a times x minus a. So if you put this on the top of the fraction, that would be equal to x minus a is equal to b minus a. Okay, of course, that's for x is greater than or equal to a, less than or equal to b, and then we want to put, so f of x would be equal to 0 if x is less than a, and that would be equal to x minus a over b minus a if x is between a and b. And of course, it's going to be equal to 1 if x is greater than b. So just always keep this idea in your mind. If you want to write down a CDF, it always starts with a 0, end up with 1. Okay, and I think I explained why in the previous videos, like I think 3.2. I think you can check it out in 3.2 if you forget. Okay, the form of CDF always start with 0, ends up with 1. Okay. All right, that's about this example. And as what I just mentioned up here, we know that if we want to find out the probability that x is less than or equal to a number, we can just plug the number back into the CDF and find the corresponding value. But if we want to find the probability x is greater than or equal to a number, we cannot do that directly. But what we need to do is we think the opposite of it, because the probability x is greater than or equal to a little x here is going to be equal to 1 minus the probability x is less than x, and which is equal to 1 minus f of x. So, and that's pretty much the idea we got over here. Using f of x to compute probabilities. Let x be a continuous random variable with a PDF of f of x and CDF, the capital F of x. Then for any number a, the probability x is greater than a is equal to 1 minus f of a. Since we don't have to worry about the boundary points, we can see that the probability x is greater than or equal to a is equal to the probability x is equal to the probability x is greater than a. Okay, because the probability of a single point is always equal to 0. And for any two numbers a and b, the probability x is greater than or equal to a, less than or equal to b is equal to f of b minus f of a. Of course, and I think I explained this in the lecture video 3.2, so I wouldn't do that again over here. The idea is very similar, and if you forget why those two are equal, you can check out that video. And we know that this would be equal to the probability x is greater than a, less than b, is equal to the probability x is greater than or equal to a, less than b, and is equal to the probability that x is greater than a, less than or equal to b. So those four probabilities are always equal to each other, because once again the probability of single point of a continuous random variable is always equal to 0. Okay, I think this part is pretty straightforward if you understand the section 3.2 well. Okay. All right. Once this makes sense to you, let's take a look at this example here. This coming from the textbook example 4.7, and the problem says given the PDF f of x is equal to 1 over 8 plus 3 over 8x. For x is greater than or equal to 0, less than or equal to 2, or 0 otherwise. And we want to find a CDF first. Okay, if we want to find the CDF, we always think of this formula here. Just f the capital F of x is equal to the integration from negative infinity to x f of y dy. So this is a general form. This is a general form of how to find the CDF with the given PDF. And then, of course, we plug the specific boundary points back into the integration here. The lower bound is 0, of course, and the upper bound could be any number between 0 and 2. So we put x over here, and then we put the form of a PDF back into the integration here. Since we are do the integration respect to y, so we're gonna have 1 over 8 plus 3 over 8 of y here. So why do we have y here? Because we have already used the x over here. We want our final answer in the terms of x. So since we use the x over here already, so we use the y here in the inside of the integration. And then, of course, if we let's take a look at how to do the calculation here. What we need to do is just apply the power rule, I think. Yes. So that would be 1 over 8y plus 3 over 16y squared, and then from 0 to x. So if we plug x back into here, we're going to have x over 8 plus 3 over 16 x squared. And if we plug 0 back into here, we're going to 0. So we get a minus 0, and we don't have to do that over here because it wouldn't change anything. And this is the form of the CDF when x is between 0 and 2. And then we want to put the CDF in a general form. Thus, f of x, that would be equal to x over 8 plus 3 over 16 x squared when x is between 0 and 2. And of course, it's going to be equal to 0 when x is less than 0. And it's going to be equal to 1 when x is greater than 2. So always keep this idea in your mind that the form of the CDF always starts with 0, ends up with 1, okay? So the 1 over here represents the sum of all probabilities in the given interval here. That's why it's equal to 1. All right, I wish this makes sense to you. And if it does, let's move forward. And this is the continuation of the example for point 7. Is asking that what is the median of the data set? We're looking for the median m. So if we want to find the median, we gotta know what is median. Okay, based on what we learned in chapter 1, I think we know that median is splitting the whole data set into bottom 50% and top 50%. In other words, the probability to the left of the median would be equal to the probability to the right of the median would be equal to 0.5 because the median split the whole data set into 50-50. So we are looking for a number, we are looking for x value that will make the CDF equal to 0.5. Okay? That's the idea here. We want to find an x value that will make the CDF equal to 0.5. Okay, that would be median. So what do we want to do here? We just need to do a set up equation. 1 over 8x plus 3 over 16 x squared. That would be equal to 0.5. Right? So because we're looking for x value that will make the CDF is equal to 0.5. Now we can set up an equation like this over here. And then we just need to solve for x values over here. What we need to do here is first of all, we want to get rid of the fractions. So multiply 16 by both sides of the equation. We're going to have 2x plus 3x squared, and this equal to 8. And then we move 8 to the other side. We're going to have 3x squared plus 2x minus 8 is equal to 0. And then if you factor this out, it's going to be equal to 3x minus 2 times x plus 2 is equal to 0. So from the first factor form, we have x is equal to 4 over 3, or x is equal to -2. But we know that x got to be between 0 and 2. X got to be between 0 and 2. So this one doesn't make sense. So we get rid of this root here, and then we can make the conclusion that the median is equal to 4 over 3. Okay, so that's pretty how to find the median, and you will definitely see something like this in the homework set. And similarly, what if I want you to find the 75th percentile? So what if I want to find the 75th percentile? So let's take a look at what is 75th percentile. So based on what we learned, in the previous chapters, we know that get rid of that. The 75th percentile split the whole data set into the bottom of 75% and the top 25%, right? Okay, if I say, okay, I will set that the value of the 75th percentile is equal to x. Let me get rid of this. If I set that the value of a 75th percentile is equal to x, then we know that the probability x is less than equal to little x would be equal to 0.75. Okay? And then we just need to, if we want to find the 75th percentile, we're looking for an x value that will make the CDF equal to 0.75. So what we need to do is we just need to set up new equation, which is 1 over 8x plus 3 over 16x squared, which is equal to 0.75. Okay? And I leave the calculation here for you guys because I just came up with the idea when I was recording this video, and I didn't do the calculations in advance. So I just want to show you the idea here. So whatever you want to find out the median or you want to find a percentile, just think of the idea of a CDF. Okay, if you are looking for median, you are looking for x value that will make the CDF equal to 0.5. If you are looking for something like a 75th percentile, you are looking for an x value which will make the CDF equal to 0.75. Okay, I hope this makes sense to you. Now let's take a look at once this makes sense. Let's take a look at this proposition here, how to obtain the PDF from the CDF. If x is a continuous random variable with PDF f of x and the CDF, the capital F of x, then at every x at which the derivative fx prime exists, then we're going to have the derivative of the CDF is equal to the PDF. Okay, now once this makes sense to you, let's take a look at the previous example. Based on what we got here, we know that f of x, if I gave you that f of x is equal to 1 over 8x plus 3 over 16 x squared, for x is greater than or equal to 0, less than or equal to 2, and then 0, x is less than 0, and 1, x is greater than 2. So if I gave you a PDF of x like this, I know I want to find if I gave the CDF of the random variable like this, I want to find the PDF f of x. So based on the proposition here, we know little f of x is equal to the first derivative of the CDF. So which is the derivative of this thing here. So 1 over 8x plus 3 over 16x squared. Derivative of that. So what do we need to do here? Just apply the power rule, which is 1 over 8 plus 3 over 8x. And if you just put it in a general form, f of x would be equal to 1 over 8 plus 3 over 8x if x is greater than 0, less than or equal to 2, and then 0 otherwise. So why is 0? So if we think of the interval x is greater than 2, we have that f of x, the CDF is equal to constant number, and we know that the derivative of a constant number is 0. So of course the derivative of 1 is 0, and derivative of 0 is going to be equal to 0 as well. That's why we have that the PDF is going to be equal to 0 otherwise. And of course the PDF here is the exactly same thing as given in the problem here. Okay? Exact same thing. So basically, if the problem gives you a PDF, you do the integration to find the CDF. And if the problems give you the CDF, you do the derivative to find the PDF. Okay, that's the idea here. I wish that makes sense to you. And once this makes sense to you, let's take a look at the expected values. So before talking about the expected values of continuous random variable, let's take a look at how did we find the expected values of discrete random variables. So if it's discrete random variables, we have expected value is equal to sum of x in the all the possible values xi times p of xi, right? That's how we find the expected values when we are dealing with a discrete random variable. And as what I just mentioned, if we're dealing with a continuous random variable, the only difference that instead of doing the summation here, we are doing the integration. Okay, so the expected value or mean value of continuous random variable is PDF f of x. So mu fx is mu sub x, the mu is going to be equal to, of course you can use mu as well. Mu or mu sub x or e of x is going to be equal to, in general, the integration from negative infinity to positive infinity, x times f of x dx. Okay, so very similar to the idea that the expected value of discrete random variable. Instead of a summation, we're doing the integration here. So in general, we use the negative infinity, positive infinity here, but different problems will give us different specific intervals, and we're gonna think of it specifically. But in general, we use negative infinity to positive infinity, because for continuous random variable in general, x could be any number on the number line. All right, that's pretty much how to find the expected values. So let's take a look at the example here. So given the PDF that f of x is equal to 3 over 2 times 1 minus x squared if x is greater than 0, less than or equal to 1, and we want to find the expected value. So this is pretty straightforward. If we want to find expected value with given the PDF, in general, we do negative infinity to positive infinity, x f of x dx. So specifically, the interval of x values over here is from 0 to 1, and then x times f of x is here. We bring it back into the integration here. That would be 3 over 2, 1 minus x squared dx. Okay? And then we just go ahead to do the calculation here. That would be equal to integration from 0 to 1. And if we distribute this thing to the parentheses, it's going to be 3 over 2x minus 3 over 2x squared dx. And then that would be equal to, we just need to apply the power rule, right? So that would be 3 over 4x squared minus 1 over 2x cubed. And then, I'm sorry, I made a mistake here. So it should be, this is not right. Because if we dispute, power is not right, because if we distribute this into the parentheses, we're going to have 3 over 2x times x squared, so it's going to be x cubed here. And then this would be equal to 3 over 4x squared minus 3 over 8x to the 4th. So just like the power rule, from 0 to 1, if you plug the upper bound back into that, it's going to be 3 over 4 minus 3 over 8. And if you plug 0 back into inside of this part here, you got 0. So again, minus 0. So the answer would be 3/8. And that's how we find the expected value of a continuous random variable with the given PDF. Okay, so it's similar as what I mentioned I think it's in the video 3.2. I think very similar to the idea mentioned in that video. And I wouldn't go over the proof again here because the idea is very similar, and the only difference is that instead of doing the summation, we're doing the integration here. Okay, so actually this is a solution here, which is exactly the same thing as what we did up here. Now let's take a look at it for quick, just to read it over. E of x in general, that would be equal to negative infinity to positive infinity, x times f of x. And since the specific interval here is from 0 to 1, so that would be x times f of x. And then we do the calculation and got the same answer, 3/8. Actually, we don't need this here. All right, if this makes sense to you, let's take a look at how to find the expected value of a function. And for the discrete random variable, we know that if we're looking for the expected value of a function e of h of x, so that would be equal to sum of h of x times p of x. Of course, p of x is the PMF, right? And for x in the all possible values. And the same idea, similar idea here. I wouldn't say exactly the same thing. I mean, I would say that the similar idea here, instead of doing the summation, we're doing the integration here. So if x is a continuous random variable with PDF f of x and h of x is any function of x, then the expected value of h of x is going to be equal to negative infinity, positive infinity, h of x times f of x dx. Okay, this is a general form, of course. Different problems will give us different specific intervals, of course. Now, let's take a look at this. This is the continuation of the previous example we went over here. So in this case, we're looking for the expected value of x squared. So, of course, x squared is a function of x, right? It's a function of x. So we have that e of x squared, that would be equal to negative infinity to positive infinity. So the function here is x squared times f of x. So what all we need to do is just apply the formula given here. Since h of x over here is x squared, so we just use x squared over there. And then we just go ahead and plug the lower and upper boundary of the interval and the expression of the PDF. So that would be equal to integral from 0 to 1 x squared times 3/2 times 1 minus x squared dx. And then we distribute those two things into the parentheses. We're gonna have 3/2 x squared minus 3/2 x to the fourth from 0 to 1 dx, of course. All right, that would be equal to 1/2 x cubed and then minus 3/10 x to the fifth from 0 to 1. Okay, so what we applied here is just the power rule of integration. Once again, if you forget how to do the integrations, you get a kind of a review on it, because you will definitely see something about the integrations in chapter 4 and in chapter 5, and this is the most important knowledge points in this whole class. Okay, chapter 3, chapter 4, and chapter 5 are the most important parts in this class. And then we just need to go ahead to finish the calculation here. We plug the 1 back into here. That would be 1/2 minus 3/10. If we plug 0 back into here, we get a minus 0. So the answer would be equal to 1/5. So that's pretty much how to find the expected value of x squared, okay? So of course, if you want to find the expected value of let's say 2x plus 1. Of course, you don't have to the whole integration here. That would be equal to 2 times e of x plus 1, okay? So we can apply the linearity of the expected values over here as well. Or let's say, for example, if you want to find the expected value of x, let's say x cube, we just it's just the same idea. That would be equal to negative infinity, positive infinity, x cube f of x dx. So I wouldn't go over the calculation here again because I just came up this thing over here, because I just wanna let you know that whatever the expression inside of the parenthesis is just the very similar idea as what we just went over here. Okay. All right. So once this makes sense to you, let's take a look at the variance. So the variance of continuous random variable x with PDF f of x and the mean value mu is sigma squared is equal to v of x is the integration from negative infinity to positive infinity x minus mu squared times f of x is equal to e of x minus mu squared. Because since we know that variance, no, I think it might be good to use sigma square. Sigma square is equal to the sum of x minus mu square, x minus mu square over n. Yeah, I think I proved this in the previous video, and so if we set yi is equal to xi minus mu square, so on the top we're gonna have sum of yi over n, so that would be equal to e of expected yi, expected value of y, and of course this is equal to expected value of x minus mu square. Okay. So of course, if we have this e of x minus mu squared, this is going to be equal to, we just need to apply the formula we just went over here. Of course, in this case, h of x is equal to x minus mu squared, right? So what we need to do is just negative infinity to positive infinity, x minus mu squared times f of x, and then dx, which is exactly the same thing as what we got here. And of course, the standard deviation is going to be equal to the square root of variance. And the proposition of variance also applies to the continuous random variable as well. The variance v of x is equal to e of x squared minus the quantity square of the expected value of x. And this proposition is very important, because I got some emails from some of you. To ask how to find e of x squared. Of course, if you want to find e of x squared, you can do the calculation like what we just went over here, or you can also say e of x squared is equal to the variance plus the quantity square of the expected value. Okay, this proposition is very important. If you remember this proposition, it's gonna save you a lot of time. Now let's just take a look at the examples we just went over. So still, this example here, f of x is equal to that, okay? And then we want to find the variance. Variance is equal to e of x squared minus the quantity square of expected value. And we have that e of x squared is equal to 1 over 5. Yeah, just 1 over 5. There's no square over here, so we don't need the parentheses here. So since e of x squared is 1 over 5, and then minus the quantity square of the expected value. The expected value is 3 over 8. That would be the square of 3 over 8, 3 over 8 squared. Okay? and then you just this is a 1/5, and then minus a 9/64, like that. And I will leave the calculation for you guys to do this, because I just came up this idea when I was recording that idea, and when I was recording this video, and I didn't do the calculation in advance, so I don't want to spend too much time on going over the calculation here. But you on whatever on the homework problems or on the test, you need to give me the simplified final answer. Okay, you just need to type this in your calculator and get a final answer. So that's pretty much how to find the variance. So if you want to find the variance, you may want to think of, because this formula is just of course you can always apply this formula, but sometimes it's just a too long calculation to do. So what I just recommend you is just to remember this proposition here, because it's gonna I mean just think of this formula first. Once this works, it's gonna save you a lot of time. So based on what we just went over, we can tell that actually the properties of continuous random variables are very similar to the properties of the discrete random variables. So once again, the main difference is that for some calculation part, instead of when we are dealing with the continuous random variable, instead of doing summation, when we are dealing with the discrete random variable, we are doing the integration here. So once that is clear to you, I think you'll be fine. Okay, and always keep the idea that the CDF always start with 0 and ends with 1. All right, that's pretty much all about 4.2.